Hi, this is the second part of ACO or and colony optimization, part two. As promised, this is a practical part of how you're implementing ACO on real life example, which is travel salesperson. Travel salesperson actually is a common artificial intelligence problem in the field of artificial intelligence. This problem is common problem and usually any algorithm, if you want to test it, then this could be a benchmark. This TSP problem is a benchmark for that one. So by the end of the class, we will be able to understand ACO and how you use it for travel salesperson, uh, and also how we compute visibility and transition probabilities, and also applying roulette wheel selection and how we can modify Fairmont after a complete iteration. So here, initialization, we start with randomly placing ants in cities, initialize the Fairmonts. Each Fairmont could be one, uh, and how we can build a tour by repeatedly selecting the next city using this formula. Here, this is the Fairmont intensity, and this is the visibility or visibility, and here feasible cities that and K can go through. Now, here, deposit Fairmont, how much ant can place Fairmont on the path, 1 over LK, the change of the Fairmont or deposit of the Fairmont is 1 over K, and K is the ant K's toe length. Update rule, Fairmont equals 1 minus P multiplied by Fairmont plus the sum of the um, Fairmont deposit Fairmont. Okay, that's the sum of the deposit Fairmont, that formula. So this is the problem that we have. We have 5 cities, 1, 2, 3, 4, 5, and 1 to 1, nothing, 0. 1 to 2 is 10. That's here. Um, 1 to 3 is 12. This one here, that's 12. 1 to 3. Uh, 1 to 4, 1 to 4, this one, 11. And 1 to 5, this one is 14. Likewise, uh, 2 to 1 is 10, that one. 2 to 1 is 10, this one. And 2 to 2 is 0, nothing here. 2 to 2 is 0. And 2 to 3, 2 to 3 is 13. That is 2 to 3 is 13. 2 to 4 is 15. That is 2 to 4 is 15. 2 to 5 is 8. That is 8 here. That's 8, and so on and so forth. So this matrix represents the diagram of travel salesperson. So we're trying to solve this one. We will have 3 ants, 3 agents. Alpha is 1, Fairmont's importance, and visibility is 2, beta, evaporation rate 0.5. We start as a constant throughout. Initial formula is 1, we start. So here is the how we find the uh, visibility. So visibility is 1 over the distance that we have. For example, the first distance was 0, 1 over 0 is 0, 1 over 10 is zero point 0.1, and 1 over here, 1 over 12 is this one, and 1 over 11 is this one, 0.09, and so on and so forth. So the distance, 1 over the distance, ij is the visibility of the path. Now, initial Fermat matrix, we said that we initialize on each segment or each edge, 1, 1, 1, 1, 1, 1. It's a matrix of 1 to all edges equally. That's initialization that we start. And we start with city one. Okay, we start with city one. So if we start with city one, then city one cannot be visited. If city one cannot be visited, then all city one would be zero. Everything in city one will be zero. So let's do the probability calculation from city one to city two. That's the formula, which is Fairmont multiplied by visibility. Visibility, we find it for 1 to 2.1 multiplied by Fairmont's 1. And the beta is 2, by the way, beta is 2. So that's 2. And alpha is 1. That is alpha power 1, power 1, power 1. So simply we can find visibility multiplied by the Fairmont. We will find the probability. So 1 to 2, we find 0.01 probability. 1 to 3, find 0.0069 probability. 1 to 4, 0.083, and likewise 5, 0.0051. Now, we sum all these probabilities and we find 0.03. Now, each city, for example, the 1 to 2.01 over the sum, we'll get this one. 1 to 3 is 0.069 divided by the sum, and that's we get. So that, I mean, this is, sorry, these are the probabilities from 1 to 2. This is 1 to 3, 1 to 4, 1 to 5. Each one of them over the sum, and each one of them over the sum. So each one of them over the sum. That's how we got it. Now, they should, I mean, if you sum them all up, they should get 1. Okay, so 100%. Okay, 100% probabilities, because probability is from 0 to 1. So all of them should be 1. Now, so cumulative probability, if we add this to this, it'll be 0.557, and then 0.557, if we add it to this, it'll be point. So this added to this, it'll be 0.557, and 0.557 plus this one, it'll be 0.8316. 0.8316 add to 0.2739, you will have 1. So each city each city will be added cumulative. So this add to this one, then the sum of this one will be add to this one, and the sum of this two will be add to this one, and all of them should be 1. That's what we got. Now we need to toss a number R in between 0 and 1 and see what we get. Imagine we toss a number and it is 0.6841. That's the number that we tossed. So this number, we check it. If it is where it's located, this number. So this number, if we see the cumulative probabilities, so it's located in between, that's 0.86, so less than 0.316 and greater than 0.557. So it is here. That number is here. So therefore, if this is city 1 to 2, city 1 to 3, 1 to 4, 1 to 5, so we select 4. Why? Because the R was very close and it was between 3 and 4, between 2 and 4, so it is 4 is selected. 4 is selected. That's the answer for, I mean, which city we select based on the probability. We select the this one in between 2 and 3. That's this one, the first one, and the third one. So we will select city 4. City 4. Now we select city 4. That's here. Now, therefore, adjusted visibility matrix, which is either we call H or this symbol, that is the visibility. We will have Fairmont kind of updated, okay? Fairmont kind of updated according to our See the 1 started, it's all 0, and 4 started. I mean, from 1 to 4, 4 selected, it became all 0. So 0 indicates that the city cannot be selected, 4 cannot be selected next time, and 1 cannot be selected next time. And then that's how we work on it. Now, and you see this is also the visibility that we found earlier, 0.0833, 0.0833. That's here, you see. Um, see, that's what we found. So, see, 1 to 3 is that one. Now, now we decided to select node 4 or city 4. So from 1 to 4, and then remaining cities we have 2, 3, 5. We have 5 cities in the problem. We started with 1, and then based on the Fairmont's probability, we selected 4. And now from 4, we either go to 4 to 2. Okay, and we have the visibility 0.06 to the beta square. That's the result. 4 to 3, we have 0.111, 1 square, you will get this much. And from 4 to 5, you will get 0.0625, according to the visibility that we have, to the power of beta, which is 2, that much. Now, we sum them all up. So you will get this one rounded. We will get this one, 0.02625. That's what we call it. And now, if we do transition probability from city 4, 0.004 over the sum, 0.004 over the sum. I mean, this one over this one, this one over this one, this one over this one, and we see the cumulative probability. And the cumulative probability, we see that from 4 to 2 is this one, from 4 to 3 is this one, from 4 to 5, this one actually 5. 5, so that's my mistake, that's 5. 4 to 2, 4 to 3, 4 to 5. So this one. Now cumulative, this one plus this, and then the sum of this 2 plus this, they all should be 1. That's what we found it. This plus this, this plus this, all 3, that should be 1. And then the cumulative, it will be 0.2136 plus 0.0107 and 1. So how we found cumulative, by the way, it is this part plus this part. We'll get 0.87, 87 something here. That's the figure, 8107, 0.8107, and 0.8107. Let me get it now. 0.8107 plus this, the leftover. So 0.8107 plus 0.1893. By the way, I'm trying to find the cumulative. Okay, that's the how cumulative came. So here the cumulative came. 0.2136 started and then became 0.8107 and then 1. So we toss a number again, random number between 0 and 1. We will get 0.4. Imagine, assume that we receive 0.4024. We check this number where it's located. Well, it's located in here, in between these two. Okay, in between these two. So that is 0.232136, and that is 0.8107. So the number 0.4 is located between this here. Therefore, we will select node 3. Node 3 has been selected. We will continue doing this one until we will find the path. And I mean, imagine that we all did all the process. we will find ant1, that's the path, 1, 4, 3, 5, 2, 1. I mean, we will arrive at the 1. So that is the path distance. From the diagram, we have 11, 9 plus 14. 1 to 4 is 11, and 4 to 3 is 9. 3 to 5 is 14. 5 to 2 is 8, and 2 to 1 is 10. So 52, the total cost. Likewise, so on and so forth. And 2, we have 1, 4, 2, 5, 3, 1. So all of them, the three ants, they started with 1, 4, 1, 4. And this is the shortest path that we have. So this 52 is selected here. Now 60 is higher, and the other one 60. So ant 1 is the visit for all cities with a different path and the shortest path. Now we try to find the pheromone deposit. We say pheromone deposit 1 over L of each ant. Okay, so for ant 1, 1 over 52, that much. For ant 2, the cost is 60. 1 over 60 is this much. And for ant 3, 1 over 60 is this much. Now, here, pheromone evaporation and evaporation happens in any, you see, a path that's neglected, the ants will not visit, will not trial again. So we reduce the pheromone by pheromone equals 1 minus P multiplied by current pheromones, and the evaporation rate is 0.5. So 1 minus 0.5 multiplied by 1. So the pheromones for each edge in the graph will be 0.5. So that is the graph for the pheromones that we have. It was all 1 we started, remember, and now became all 0.5 because 1 minus 0.5 is 0.5. So we got it. Now evaporation means that old information fades, new good paths can dominate, and without evaporation, ACO becomes stubborn and with commitment issues. Now here the how we do the deposit, how we change the deposit, and how we update the pheromones. So now how we did the deposit, we found the deposit, and how we update it. So for pheromones for 1 to 4, it will be 0.5, the evaporation that happens, plus the for the ant 1 and ant 2 and ant 3, all of them collected, we find 1, 4. Likewise, if you want to find pheromones for edge 4, 3, it was evaporated. It was 1 minus 0.5, it became 0.5, and 0.5 plus the ant for deposit on the ant 1, it was 0.0192. So that's the answer for it. Likewise, for H3, that's the result for the H3, same information that we do. There was no change for H3 because H3 1.5 hasn't been selected, so hasn't been used. The ant didn't go through it. So because of the probability cumulative, it wasn't selected. So the pheromone stays 0.5. It was originally 1, but 1 minus 0.5 minus 1 minus the evaporation rate, 1 minus 0.5, that's evaporation rate, P, so 0.5. So it stays 0.5 as it is. So that is more or less about how we work with ACO, and this is the matrix for after the first iteration, and you can see the ant1, how it's scored, ant2, and this is the visibility and pheromones update. This is the pheromones update for the matrix. So for iteration 1, ant 1 was selected with distance 52, and then next iteration we use updated pheromone matrix, repeat torque construction, and continue until maximum iteration or coverage or convergence is arrived. Thank you very much for this watching this video, and if you have any problem or issue, please contact me. Thank you very much.